Physics can do matrix multiplication for free. No transistor switching, no binary logic, just raw electrical current flowing through a resistor. In 2026, analog chips are outperforming NVIDIA's best GPU by 1,000 times in throughput and using 1,000 times less energy per operation. After analyzing 42 sources including papers from Nature, Science, and IBM Research, I'm going to break down exactly how Memristor crossbar arrays bypass the von Neumann bottleneck. I cross-referenced Mythic's claimed specs against independent coverage from Bloomberg and Quantum Zeitgeist. The numbers are consistent. No sponsors, no bias, just verified engineering data. Here's the problem nobody talks about. In conventional computing architectures, 62 to 80% of total system energy is wasted just moving data between memory and processor. For large language model inference, transferring weights via PCI Express buses consumes roughly 100 times more energy than the actual arithmetic operations. The math is cheap. The commute is expensive. Even the fastest GPUs spend over 60% of their time idle, just waiting for data to arrive from memory despite multiple cache levels. Computation and memory live in separate physical locations. Every single multiply-accumulate operation requires a round trip. This is the von Neumann bottleneck, named after the 1945 architecture that separated processing from storage. So what if we could eliminate that movement entirely? The key idea: instead of encoding everything as binary, use continuous physical quantities, voltages and currents, to represent numbers directly. Ohm's law says current equals voltage times conductance. That is multiplication. If you apply a voltage representing your input, and the wire has a conductance representing your weight, the current is the product. Kirchhoff's current law says currents sum at a shared wire. That is addition. When multiple currents flow into a single column, they automatically accumulate. That's your summation, for free. Now put it together in a Memristor crossbar array. Store your weight matrix as conductance values at each cross point. Read the output currents on the columns. You get a full vector matrix multiplication in a single step. A 2x2 crossbar with input voltages of 0.20 volts and 0.10 volts and conductances of 1 and 2 millisiemens instantly produces output currents of 0.40 and 0.20 milliamps. Physics just does it. Imagine if instead of writing a sorting algorithm, you just dropped objects into water and let gravity sort them by density. Analog computing lets physics execute the algorithm. Memristors are two-terminal devices whose resistance remembers the history of voltage applied to them, just like a synapse strengthens or weakens based on activity. Computing where you store. Neural network weights are physically encoded as conductance values. The weight is the hardware. No fetching from DRAM, no data movement whatsoever. This eliminates the von Neumann bottleneck entirely. In current mode sub-threshold design, multiplication requires only 2 transistors. Energy per operation drops to as low as 1.6 femtojoules. Your brain performs at this level on just 20 watts. Let's talk real results. According to peer-reviewed benchmarks from Nature Electronics, the Peking University team's RRAM chip achieved 1,000 times higher throughput and 100 times better energy efficiency than GPU. Mythic's analog processing units, now shipping in 2026, operate at 17 femtojoules per operation, 1,000 times less energy than GPU. They achieve 120 trillion operations per second per watt. IBM's NorthPole chip delivers 47 times faster and 73 times more energy-efficient performance for large language model inference, achieving sub-1 millisecond latency per token. Now let's be honest about limitations. Training is still digital territory. Analog chips excel at inference, but training requires precise iterative weight updates that Memristors can't yet handle reliably. Device variability and noise remain real challenges. No 2 Memristors are perfectly identical. However, neural networks are inherently noise-tolerant since weights are approximate by nature. So here's where we stand. Analog computing exploits physics, Ohm's law and Kirchhoff's law, to perform matrix operations in a single step without data movement. We're witnessing computing come full circle. If you're a CS student trying to understand where hardware is heading, subscribe. I break down emerging architectures from peer-reviewed sources so you don't have to. Thanks for watching.